All right, in the previous video, we talked a little bit about linear independence, but now we need to give it a formal definition. And as far as the theoretical or conceptual parts of linear algebra go, this is probably the most important concept. So let's look at this. We're going to build up the definition here. You're given a set of vectors v1, v2 up to vk from the vector space V, and we set up this equation. This side over here is just an arbitrary linear combination of those vectors. And we set it equal to the zero vector, which, depending on your, if you're dealing in the R2, this would be your zero vector. If you're dealing in R3, it would have 3, and so on. But if you look at this, there's always going to be what's called the trivial solution. If you put in 0 for each one of these C's, then you're definitely going to get the zero vector out of it. And if that's the only solution you get, we say that these vectors are linearly independent. If there's a non-trivial solution, that's a solution where at least one of your coefficients is non-zero, then S is called linearly dependent. So let's look at this a few examples. Show that this set is linearly independent. All right. So let's see. I'll do this one out sort of the long way. So 1, 3, 4 plus C2 times 3, 3, 3 plus C3 times 1, 1, 7. And we set that equal to the zero vector. And we're supposed to show that this is linearly independent. What this means is we need to show that this only has the trivial solution. So what I'm going to do is rewrite it as an augmented matrix. 1, 3, 4, 3, 3, 3, 1, 1, 7, augmented with zeros. Now I'm going to enter that into Octave. That looks good. Well, now when I reproduce this, notice it gives me this. And if you read this off, this is the C1 column, C2, and C3. That top line gives you C1 is 0. The second line gives you C2 is 0. The third line gives you C3 is 0. So all we get is the trivial solution. Therefore, they are linearly independent. All right. Let's see this fact here. It says if the set is linearly dependent, then at least one of the vectors can be written as a linear combination of the others. So let's look at this next example. Show that this set is not linearly independent. Then express one of the vectors as a linear combination of the others. All right, so again, what I'll do is I'll say C1 times 4, 5, 1. I'm just going to go ahead and convert this into a column. Plus C2 times 1, negative 4, 7. Plus, or no, not plus, equals 3, 2, 3. All right, so I can rewrite that as an augmented matrix. Oh, wait a second. That's not what I want to do. Because first up it's saying show that they're not linearly independent. So I need to set up the 3 of these like that. And I need to show that this has more than one solution. And I said more than one a second ago, and then I wrote down non-trivial solutions. But that's the same thing. We know that this has the solution where all all three of those coefficients is 0. But what we need to do is show that it has non-trivial solutions as well. So I'm just going to put this into octave as a augmented matrix. And then we'll row reduce it. So what do we have here? 4, 1, 3, 0. 5, negative 4, 2, 0. And then 1, 7, 3, 0. Looks good. Now when I row reduce it, we get this. Let's see, 1, 0, 2/3, 0, 0, 1, 1/3, 0, then 0, 0, 0, 0. All right, so we have what this gives us now is a general solution. So there are a couple of ways you could do this. To show that it's not linearly independent, we can say this has infinitely many solutions. And that's because we could write this out, remember, as a parametric solution. We could say that coefficient 1 is equal to negative 2/3 coefficient 3. Coefficient 2 is negative 1/3 coefficient 3. Coefficient 3 is a free variable, so it can just be whatever it wants to be. So infinitely many solutions, therefore it's linearly dependent. Okay, what about that other part of the question? So we've shown that it's not linearly independent. Express one of the vectors as a linear combination of the others. That's where, that's what I started sort of mindlessly setting up a minute ago. I'm going to duplicate this. Oops. Duplicate. I'm going to bring this down here. And if I wanted to set this up as, I'm going to set this third part up as a, I'm going to set this third vector as a linear combination of the first two. So I'm going to set that up. And then that's going to give me this matrix. Now, notice this matrix, it's really the same one that I had above. It's just we don't have those zeros on the end now, and the augment line is moved over. So when I row reduce this, I get the same thing. 1, 0, 2/3, 0, 1, 1/3, 0, 0, 0. And what that tells me is C1 is 2/3, C2 is 2/3. Write a squiggly across here. And so I can write that third vector here as a linear combination of these two by saying, let's see, it was 2/3 and 1/3. I miscopied that. So I can rewrite this as 2/3 of 451 plus 1/3 of 1, negative 47 equals 323. So that's kind of small and crammed in there, but this is the answer to the second part of this, where it says write one of the vectors as a linear combination of the others. Let's see, we've got several more, or we've got 2 more examples. I'll put those in the next video.